Good morning, friends. Let's continue our discussion about the OMS that we are building, a dummy type of OMS. So in the previous video, we learned that how we built a single-threaded blocking OMS, which means that there is only one thread which is listening on this accept method to make it a server socket, which is blocked here, and listening for the client connections. As soon as a client sends a connection, a socket is created. So the same thread which was listening here, it has to handle it. So handling, as we also benchmarked it, that each of these individual steps, it took 1 second. For example, creating the request from the socket, and then creating an order of it, out of it, and then validating it, enriching, and etc. It all took 1 second. And after that, as soon as the thread is served, the client is served, the same thread which has been listening on the server socket, that will complete it here and then go back here, and it go in the while loop. It's not closed yet. Then again it will start listening. The caveat here, the biggest caveat here is that, as we discussed in the last video as well, that each of the client requests which are like pending in the network queue, that has to wait until the previous client has been served or not. So in this case, it has to wait for every 6 seconds for the next client to be served. Therefore, it will take around 6 seconds to complete one request and send the order to downstream if no error. And it also means that if 3 requests arrive at the same time, it will take 6 plus 6 plus 6 is equal to 18 seconds to fulfill them at 6 seconds per request sequentially. So this is like the design which nobody implements right now. It's just for the theoretical purpose. So there's a very quick upgrade on this, that how we can improve this. We can create a thread per client OMS. So what we mean is that the thread which is waiting on it, right? This at the accept method. So as soon as the client is connecting to our server, in that case, when the socket is created, at the same time we immediately create a new thread which handles that client. And because this is actually asynchronous type of thing, that for each client that is connected to us, we create a new thread on the fly, and then it's that thread would be handling it. So the thread which is actually accepting here, which was blocked, it can resume here in the while block because it's not closed yet. It will again start accepting for the next client. In this way, so now we are delegating the listening thread. We are delegating that all the handling of that particular client socket request to a separate thread. That's why this is a much better improvement over the previous single-threaded OMS that we built. So looking back in this code, so only change which we have done between this and this is about this part, that handling of the socket. Instead of the same thread which is accepting here and then handling the request, what we have done here is that we are going to create a new thread every time. And this will actually create a platform thread, which are limited in nature. That as we have learned previously, that each of the platform thread that we create, that are actually a wrapper over the OS kernel thread. And those OS kernel threads are limited in amount of the virtual cores that we have in our system. For example, if I have got a 4 CPU system, in 4 physical CPU, and there might be 8 or more than that virtual cores because of hyper-threading technology. So that's why but the point here is that there are limited number of OS kernel threads, and that's why there are limited number of platform threads which can be operating in our system at a time. And if we are creating more platform threads as compared to the virtual cores, then the context switch will happen. That's where the threads have to move across and then do a context switch, so that another platform thread, can take over that virtual core thread and perform its operation on the CPU. So that's why, this design is good, that we are creating a new thread, making it like each of the client independent of the other client requests. But as it's just suppose that if there are so many clients, thousands of clients, and so in that case, if you're creating so many number of virtual threads, there would be a limitation there that at a point we'll find that there are not enough threads to be created because of the OS limitation, and that's why our system will crash. So we'll see this example. Let's go through it once more. So here, just look at it, that we are having the main thread, which is actually listening on this. And then after that, we have got for each of the client requests which is created. So whenever this accept returns, there's a socket already being created by the thread. And now to handle that request, because this is the handle part, there we are creating a new thread, and then we are actually identifying a client by a counter. And after that, it's exactly same as we did in the previous single thread example, that we would be having like 1 second for each, that pass the request, create the order out of it, then validate the order, and reach the order, process the order. If you just look at one of them, so you're just waiting for 1 second. This is just a dummy implementation that it is going to take around 1 second. So from here to here, it will take 6 seconds. 1, 2, 3, 4, 5, 6. Yeah. And so this is for each of the client socket that has been created, and for each of the client requests that we are listening here. But the only difference is that we have separated the listening part and the handling part into separate threads. So as we have separated out the listening part and the handling part in separate thread, so one thing is that definitely for if there are 3 client requests sending a request at the same time, so as compared to the single threaded server where it was taking like 6 seconds for each request and it was taking 18 seconds in total for 3 requests, now it will take, because all the 3 handling part is done parallelly at the same time, that's why it the latency reduced to serve, or the throughput reduces from 18 seconds to 6 seconds for 3 client requests. So it means that 3 client requests could be served at the same time within 6 seconds. So the throughput is definitely increased here. And because there are all requests are from separate users are completely independent of each other. So this is a perfect example that we can actually modify our server program into thread per request style. Okay, but the only caveat, as we learned, that it's limited number of threads that can be created, platform thread in the pre-Java 21 versions. So let's run this program and see that how it works. So I will first of all let me start this program. So I click this run button here, and then I have created the socket client. I will use the same socket client that I created before, in which I'm able to create the number of socket connections at the same time based on the arguments. So for example, here you can see that right now our thread per client OMS is listening on port this one. So let me actually start just for the 4 clients connection at the same time. So we expect that even for the 4 client connections, it should be very quick. It should be taking only 6 seconds because all the 4 are run at the same time. Now let's look at this. Now here we can see that it's already done, and it's quite fast. And each of the requests itself, it took only like 6 seconds. But all the 4 requests, all the 4 client connections were done simultaneously. So the total amount of time which it took was only 6 seconds. Now again, so we have got these 4 clients, but as we mentioned many times that now it's because it's getting platform threads, is going to be quite there is a limitation that how many threads that we can create at a time. So I've created another socket client program which will try to connect 10,000 or 100,000 times. And let's see, because of the limitation, whether it breaks or not. So let me just show this 100,000. So I've created this 100,000 one. So if I just look at these configurations here, so for 100,000, it's actually 100,000 of client connections that will be done immediately. So this is what we want, and we try to it's like a sort of a stress test that how many threads that we can create and can be handled by the server. So we'll see that 100,000 is quite a big amount, and those number of threads cannot be supported if we are just using the platform threads. So let me run this and see. So I'm just going to run this 100,000 client connections at the same time. So here is our thread per client OMS output console. The previous one, the output that you are seeing is for the 4 client connections that we did. It happened at the same time for 6 seconds. So for 100,000, so you can see that after a certain point, the number of threads were refused to be created by the socket client, because here, as we can see that the amount of threshold threads, the platform threads that we can create, that has got a limitation. And after, say, I think 416, after 416 only, our connection got down by saying that connection refused, because those number of threads cannot be created here. We cannot create every time on a fly because of the platform thread that we are creating. So guys, let's revise what we have learned today. So we actually moved from the single threaded server to a thread per client OMS. We are creating a new thread every time to handle the request. And that's why, I mean, for the small number of requests, because definitely we can create a certain number of platform threads at a time. So that actually helped us to improve the throughput tremendously. I mean, each of the requests can be served at the same time concurrently, and that's why the throughput was increased. Now, there are few caveats that we need to discuss before we move on to the next approach for this server. So within a single request in the handle method, the parsing, validating, and persisting and sending the order to downstream is all done in the same thread. So still, I mean, of course, I mean, we have got a separate thread to handle the request, but within that handling part also, we are doing it in the same thread, which can be improved. There's a scope of improvement here in this handle part. So when we have one thread, the same thread which is handling this, it has to do all these 6 steps, which is taking 1 second each in the same thread. So this is a scope where we can improve it further. And also, as we have already learned that their threads are scarce and there is a limitation imposed on the maximum number of threads which can be created in the OS, which we already discussed. So thus the design doesn't scale well when the number of client connections will increase. As you have seen that if we increase it to 100,000, in that case, 100,000 is a big amount. Even if you increase to like 10,000 or 20,000, in that case also you will see that it will break at a certain point of time, that it is unable to make the connections because of the thread limitation, number of thread limitation. So this was all about this thread per client approach, which works well when the number of client requests are less. Now we'll see that how we can improve it. So we can have thread per client and thread per order parsing OMS, which means that we are going to handle this part, that not the same thread it should be doing all these steps for handling the request. So see you all in the next video.